Sure.
Okay.
Clump together with your pen. So let's hang out here and let everybody get settled. Okay, so it is 3:30 or probably 3:31 by now. So that means it is time for one of our 3:30 after school STEM shows. And so these are shows that we've been doing as a live stream every day at 3:30 for gotta be getting pretty close to 100 consecutive days at this point, where we every day at 3:30 go live on Twitch and Facebook and YouTube and do, like I said, a little short 15, 20-ish minute show covering some sort of science topic. And so those of you who are watching on the internet right now can't see, but I've got an audience here. So this is a relatively recent development that we've started having guests back into the Science Center. And so if you happen to be around and visiting us at 3:30 on one of the days that we're open, you perhaps could come and watch one of these and maybe participate as a volunteer, or at least be tapped for some answers as I'm shouting out questions into the crowd. And so I will ask, because like I said, we have a live stream happening here, so be mindful of that for our live audience, that there is a microphone, and so the stuff that you're saying is probably or very possibly going to get picked up on the microphone for the audience online as well. And so what we are going to be talking about today is sort of it's an experiment I've never done before, but it's using some concepts that I'm pretty familiar with and that we talk about in a few of our different demos that we talk about here at the Science Center. And ultimately, the kind of core thing that this is going to be an experiment about is density. And does anybody here know what density means? Can anyone give us a quick density? See one hand over here. So he said density is kind of a hardness, and I could see how density would maybe have some effect on hardness, but that's not necessarily what exactly we're going for here. See one in the back?
Like weight or mass.
Weight or mass, and density is a relationship kind of between weight and mass. And so density is basically how much stuff you have packed into a certain amount of space. So if you have two objects that are the same volume, if one of them weighs more, the one that weighs more is more dense, long and short of it. And so generally what you'll see is that stuff that is more dense than other stuff, a more dense object will sink in an object that is less dense, and a less dense object will rise in an object that is more dense. So a helium balloon floats because it is less dense than the air around it. Get it? Got it? Easy, simple.
Yeah.
And so we're going to talk a little bit about density here to start, and we're also going to talk a little bit about states of matter and how states of matter relate to density. And so I have here a model that we use in one of our demos. And so what do we know about the states of matter? Who knows what the states of matter are?
There's three of them.
Three of them. Three basic ones. See one in the back?
Liquid, solid, and gas.
Yeah, liquid, solid, gas, solid, liquid, gas. And so the three states of matter are solid, liquid, and gas. And what we're going to talk about is how sort of density relates to that. For most things, when an object is at its most dense, when it has the most of that thing packed into the smallest amount of space, is when it's in its solid form. And so you can kind of use this as a visualization where we have the BBs in here, and you can see they're all sitting at the bottom, and really if this was a solid object, they'd be vibrating a little bit. They're not really moving a whole lot, but you have a bunch of molecules that are all packed into one small area here, not moving very much. They're pretty dense, relatively speaking, for this, whatever material we're saying this is. If you convert this to the liquid form, and how do you turn a solid into a liquid? Yes? You melt it. And so melting is the process of turning it from a solid into a liquid. So the way you would do that is add some heat to it. And so if we heat this material up and it starts melting, all of a sudden there's a little bit more energy in this whole pile of stuff, which is going to let those molecules move around a little bit more. They have a little bit more energy. They can kind of stretch their bonds that are sticking them together a little bit more. And that's going to let them move around a little bit more, take up a little bit more space, and generally be a little bit less dense. And if you keep adding more and more heat to that, what do we call it when we turn a liquid into a gas?
Big word. It's got 5 syllables.
In the back?
Evaporation.
Yes.
Evaporation. Very good. So, and you achieve this by, the way you generally you'll see this is if you boil water. So when you're boiling water, it's going from a liquid into a gas. And so when you add more heat, you add more energy to it, all of a sudden those BBs, they got a lot of energy that they can work with. They can stretch those bonds out really far, and all of a sudden they're taking up this whole space I have in here. So Once down here, the BBs are pretty densely packed onto the bottom. When they're liquid, they got a little bit more, so they're a little bit less dense. And when they're a gas, they're taking up the whole space, so they're at their least dense. Now, there are some materials where that's a little bit different. The most notable one would be water, where water is, as far as I know, the only material out there that's actually more dense in its liquid form than it is in its gas form, or in its solid form, which is something we've all seen, we've all observed. How many of you have been out on the lake this year at all, since it's become winter? And you know, we walked out onto the lake, and that's not a thing you can do most of the year, is walk out onto the lake, but we can now because there's ice on it. And what is ice?
Water.
It's water. It's water in its solid form. And if ice was more dense than the liquid water, what would happen to the ice?
It would melt.
Not quite.
Or
Yep.
it would shrink.
It would sink. Yep. So if the solid ice was more dense than the liquid water, it would all sink to the bottom, and which would be a big problem for us around here, because you know it would start at the top and it would turn into ice, and then it would sink to the bottom, and it would turn into ice, and more would sink to the bottom, and then before you know it, the whole lake would just be a big pile of ice, and stuff can't live in that. We wouldn't have an ecosystem in our lakes if that was the case. And so the reason that happens is because when ice goes from a liquid to a solid, it adopts a what we call a crystalline structure, and that's got a lot to do with sort of the electrical poles on it, how they kind of stick together. But basically the gist of it is like, this is a model of it, of what would be ice, and so each of these is a water molecule, so H2O. And so when they, like I said, have sort of a magnetic poles, so they stick together, and when they stick together, they form this really regular structure. It's got basically a bunch of air in the middle of it, so I can look right through there and see you in there. Hi. The camera too. And that's not there when it's in its liquid form, so that's why solid ice is less dense than liquid water. But density isn't something that just changes when you change between states of matter. The density of materials is always changing. I mean, I know at least one exhibit down on the exhibit floor that is really, really dependent on a certain material staying within its same state, but drastically changing in density. I'll let you guys think about that for a second while I kind of start prepping for the experiment. What's the exhibit we have down on the floor that takes advantage of changes in density of a material to work? Right down on the main exhibit floor. What do you think?
The one that has the box stuff in it and the magnets that you can move up and down.
Oh, I like where your head's at there. She's talking about the nano exhibit with the magnets, and you can move the iron particles around. And that one's interesting because that one deals with mass. I don't know if I would say that one deals with density, but that is an interesting one as far as mass and weight go. So it's close, it's similar to density, but not quite.
What was Brian just talking about? Talking about things that float, things that sink. Float, sink.
The water with the bubble.
The water with the bubble. I get that too. Because the bubble falls to the ground after it comes off. If you even manage to get a bubble that detaches, you know, it doesn't just stay in there. It sinks within the air. It goes to the floor eventually. So you're right, the bubble is more dense than the air around it, and you're making a good observation there. That's not what I was thinking of, but you found a different thing that very much does the same type of thing. What else floats down on the exhibit floor? The Bernoulli Ball. Ooh, that's another good one.
Well,
You guys are coming up with a lot more answers than I thought you would, to be honest.
you can look over there if you want, sure.
So the Bernoulli Ball works with density of moving air currents. That is what keeps it within the moving air.
Yeah, but it's not the density.
It's
not
the
demonstrate density. It demonstrates something else.
yeah,
The hot air balloon.
the hot air balloon. That's
Yeah.
exactly what we were looking at for. So we're talking about the hot air balloon, of course.
Oh, that's what I was just thinking. I was confused.
There you go. Yeah.
And so what's happening with the hot air balloon is that as you press the button and the flame turns on, the flame heats up the air, and as you're heating up the air, that air isn't turning from gas to any other form. It stays as gas. It's gas the whole time. But even as you heat up that air, it gets less dense itself too. So the hot air weighs less than the room temperature air around it, and there's enough of a difference there that it makes the balloon rise. And so we're going to try something kind of similar here, where I have in this cooler a number of different containers that I put in the freezer this morning. And so what we are going to try and do here, and like I said, this is not an experiment I've done before, so I'm a little interested to see how this will work. Find my lids.
So you haven't done it before, so it might go completely wrong.
I'm confident in the science. I'm not confident in the execution.
Okay.
But that's half the fun with this.
Bit of mystery involved.
Yep. Lids on here quick as we're pulling them out. And so I've got a couple different things of different sizes here. I think we'll start with this one. Kind of an interesting shape here. And so what I have here is an empty glass bottle that I found in the basement. It's got a plastic lid on it that was not in there when it was in the freezer. I just threw that on right now. And basically what we're going to try and do is I have a very cold bottle here because it's been in the freezer and then in the cooler. And I have a penny. And so I'm going to put the penny on top of the bottle here. And basically what I'm going to try and do is squeeze it with my hand. So I got to hold this very cold bottle for a little while. And what do we suppose I am hoping is going to happen here? If I'm...
Could you hold it over a little bit toward the cooler? And so we get a little background on it?
Yep.
Okay.
So if I sit here and I hold this, what is happening within this bottle, you think? There's no water in there, but yes, I'm warming it up. And so what is going to happen as I warm this up, do we think? Yeah.
Squeeze it so the penny will go up.
So yeah, he's saying I'm going to squeeze it. I'm not like squeezing it. I'm not making it smaller by squeezing it. It's a glass bottle. I can't like squeeze it to crush it. But as I squeeze it, as I put my hand on it, what Z back there said is right, is I'm going to make the air inside this warmer. And ideally, I'm going to make it warmer relatively rapidly here. And what is going to happen to that gas as it gets warmer? Yeah.
The ice melts.
So there might be a little ice in there that's going to melt a little bit, but it's not exactly what I'm looking for. I'm looking about the gas. Yep.
The air will expand.
It's going to expand. And if it expands enough, what do we suppose might happen to that penny? It'll move the penny. Like I said, I'm not sure if this bottle is big enough for this to work, this particular experiment to work. Said this is one I haven't tried before. Normally, every time I've seen this done, it's been done with like a glass, like Coke bottle type size thing. So, like I said, I'm trying. I brought a few different bottles of a few different sizes, and we're gonna see if we can't get at least one of them to work here. But like I said, this is kind of an experiment to see what types of bottles we can make this work with, and it's hopefully something that we can use a little bit later. So we'll see how this works. Which I would think it'd be working by now if it was gonna work. So maybe this bottle's a little too small. But actually, can I get a couple volunteers? Why don't you come up and you come up? You guys have been helping out a lot. You guys ready to have some cold hands?
I don't have cold hands.
Why don't you come around to the back here by me? And so we're going to try. You're going to have this one.
Okay.
We're going to try the same thing with the dime. And so why don't
just put my
you,
hands
yeah,
around
just
it?
grab that bottle and hold it tight and focus on putting all your warmth into it.
Oh, no. The dime. Keep the dime on.
And you're going to have this big bottle here. And I'm a little interested to see what the bigger bottle, because it's plastic.
Gotta hold still.
And I'm not sure. So you got to hold that one and warm it up, but not squeeze it too much, because if you squeeze it, you're just going to blow the air out on it. So I'm going to try with this one. So maybe you can pull the camera back a little here if we're struggling to fit everybody in. And like I said, we're trying with different size bottles, different types of bottles to see what, if any, of these actually work. Because like I said, every time I've seen this before, it's been done with a Coke bottle. And sometimes you'll see it where there's water in it that you gotta put in the bottle as well. So it's like you're watching me experiment with this in real time to see what I gotta do to make this into a demo for a show someone's paying for. And so this is supposedly kind of a classic like lumberjack trick is sort of the lore you'll hear behind this is somebody says, I can knock the penny off the thing without touching it, and you put your bottle out in the snow for a few minutes, and then you come back and you try something like this, and the penny starts dancing on top of the bottle. I said, maybe we'll see it work here, maybe we won't. But like I said, the science is good.
It looks like my barn has been like I put it on there straight.
Yeah. So, like I said, maybe not today. Maybe we got to get a different bottle. Maybe we got to get a different coin. Maybe we got to find some warmer people.
Yeah.
Did y'all get your temperatures taken when you came in?
No one was there.
Maybe you're a little chilly. It's a little chilly outside.
My palm is chilly.
Yeah. So yeah, maybe we will just call it there. So, didn't quite work this time. Like I said, that's experimenting though. You don't always get exactly the result you're looking for. It'd be nice to get a nice visual with that. But like I said, this is a principle in science that you can see in a number of places out on the exhibit floor. When I think of it, I think of the hot air balloon. But like I said, you guys came up with 3-4 other things out on the exhibit floor that all deal with density in some capacity, which I think is kind of cool. Like I said, you guys thought of a bunch of stuff that I didn't even really think of, and I work here. I'm here 40 hours a week. So, I hope even though our visual aid didn't necessarily work the way I wanted it to, you guys learned something, got to have a little bit of fun in participating there. Hopefully our audience online enjoyed the show. And thank you all for coming. And so, like I said, we are live every day at 3:30 on Facebook, YouTube, and Twitch. So twitch.tv/Headwaters Science Center, youtube.com/Headwaters Science Center, facebook.com/Headwaters Science CTR. Like I said, every day at 3:30, doing some sort of different type of science show for 15, 20, 30, depending on who it is. Maybe sometimes I'm here and I talk for 45 minutes or an hour about something. It's been known to happen. But otherwise, thank you all for watching, and come and visit us in person sometime if you're here online, or if you are here already in person. Love to have you back again sometime. And we are open right now from Friday through Monday, and so Friday, Saturday, Monday, we're open 9:30 to 5:30. And then Sunday, we're open 1 to 5:30. So, again, thank you for watching, and see you tomorrow.
Thank you.
Yep. Thank you, guys.